Hello, all you cool cats and kittens. This is Mr. Bear with Skill 23, which is conditional probability. So, we're going to start with a definition. So, when we talk about conditional probability, what we're talking about is the probability that an event B will occur given, so that's going to be really important, given that another event that we'll call A has already occurred. Oops. Sorry about that. All right, so this is a situation where the events have to be dependent. So the two events must be dependent. That's going to be really important. And we use the notation P for probability, B given A, so that little slash means given, okay? What that means is probability of event B given that event A occurred. Okay? So a two-way table is very helpful when helping us find conditional probabilities. Okay, so a two-way table, what that means is we've got two types of categories. So we have, in this case, it would be types of colleges, and we have males and females, so gender. And yes, I know there are other genders besides this today, but we're going to use male and female just as our standard ones, okay? So the table shows students by gender and by type of school in 2005. Okay, so you're going to pick a student at random. In our chart, what they tell us right now is the number of males and the number of females in the different types of schools. Okay, what we need to do first is find the totals for each row and each column. I think this is much nicer if we have those totals on here. Okay, so I'm going to find the total males, 1866 plus 4324 plus 1349. There's a total of 7,539 males in all the different types of schools. For females, it's 2462 plus 5517 plus 1954, 10,113. Now, let's find the totals of each row. So the number of people that went to two-year colleges, four-year colleges, and graduate schools. So 1866 plus 2462 makes 4328. By the way, all these values are in thousands. So these numbers, if you multiply them by 1,000, that's what the true number is. 4324 plus 5517 makes 9841. 1349 plus 1954 makes 3303. And then we need a grand total altogether. This number here in this little box that I'm making here should be the sum of the rows and the sum of the columns. Okay, so if I take 7539 plus 10,113, I get 17,652. That should be the same as if I were adding this row, or this column rather, 4328 plus 9841 plus 3303. Yep. Okay. So what we need to do is first answer the question, what is the probability of selecting a female given they went to graduate school? Okay. So what this means is we're restricting our total to just the graduate school students. So I look at my graduate schools and I had 3303 that attended graduate school. So that becomes my denominator. So 3303. And I need the females that went to graduate school. Okay, so I'm going to look for females that went to graduate school. So 1,954 females went to graduate school. Sorry, I have to make sure that I emphasize that because it might get lost that it's not all the females, it's the ones who went to graduate school. When I divide this out, okay, when I divide this out, it's about 0.59 or 59%. So the way you interpret this is 59% of those who went to graduate school were females. Okay? That doesn't mean that 59% of females go to graduate school. It means 59% of those who went to graduate school are females. Okay? Now, the probability of just a female, that means we have no conditions whatsoever. So we take our number of females, which is we add up this whole column, 10,113, and we divide that by 17,652. And when we divide that out, it's about 0.57 or 57%. Okay? All right, let's look at another situation here. It says Americans recycle increasing amounts through municipal waste collection. The table shows the collection data for 2007 in millions of tons. What is the probability that a sample of recycled waste is paper? Okay, so we're looking for the probability that we had paper given that we were talking about something that was recycled. Okay? So we first need to figure out, well, how much paper was recycled? Well, that's this 45.2. And we need to divide that by all of what we had recycled. So I need to find my total of all the recycleds. Okay, so let's go ahead and do that real quick. 45.2 plus 7.2 plus 3.2 plus 2.1 plus 21.7, which is 79.4. Okay, and so what we're going to do now is we're going to divide that out, and we get about 0.57 or 57%. So what this means is of all the things that were recycled, 57% of it was paper. Okay? All right, so there is a formula that we can use to find conditional probability for any two events, A and B, with the probability of A not being 0, probability of B given A is the probability of A and B happening at the same time, divided by the probability of A. When you think about how we did that in the last example, B would be paper and A would be recycled. So we are finding the probability of A and B, so recycled and paper, so that's the 45.2. And we divided by the probability that we had recycled, okay? So recycled, remember we added up all the recycleds, so that's how we got that probability. Let's try another example here. A utility company asked 50 of its customers whether they pay their bills online or by mail. What is the probability that a customer pays the bill online given that the customer's mail? So probability that we pay online given that we are a mail. Okay, so that's what we're calculating here. So first of all, we need to first figure out probability of online and mail divided by the probability of male. So I need to know who are my online males. So that's 12 people. And out of total males, and by male, I mean male like the gender male. So 12 plus 8 makes 20 males. Okay? So the probability here is 12/20ths, which is about 60%. Okay? Can we rearrange the conditional probability formula to help us find probabilities of dependent events? Absolutely. We know that the probability of B given A is just the probability of A and B together divided by probability of A. Well, let's say I wanted to figure out what the probability of A and B is. If I solve this equation for that, I multiply both sides by the probability of A. And the probability of A and B is just the probability of A times the conditional probability of B given A. Okay? All right. And we're going to use that idea in the last example here, which did not, where is it? There it is. I was like, wait a minute. All right, so using a tree diagram. A school system compiled the following information from a survey it sent to people who were juniors 10 years earlier. Okay, so 85% of the students graduated from high school. Of those students who graduated from high school, 90% are happy with their present jobs. And of the students who did not graduate from high school, 60% are happy with their current jobs. All right, so what is the probability that a person from the junior class 10 years ago graduated from high school and is happy with his or her present job? All right, I'm going to use some letters here. Okay, so G means graduated. NG means not graduated. Kind of fitting considering that we use NG to mean not getting credit for a course. You get enough NGs, you won't be able to graduate. Okay, then we are going to use H for happy with present job. And we're going to use NH for not happy with present job. All right, so what we're going to do is we are going to make a tree branch here, tree diagram. We're going to start over at the beginning, and we have two types of people, graduates and non-graduates, okay? We were told that 85% of all the students from that class graduated. So the probability that you graduate is 0.85. That goes to show that that means that 15% of the class didn't graduate. So those who didn't graduate, they didn't tell us that, but just know that graduate or non-graduate, those are your only options. You can't have a different option than this. So those are your probabilities that you either graduate or not graduate. Now, we also need to talk about the probability that we were happy versus not happy. So graduates can be happy or not happy, but our non-graduates can also be happy or not happy. Okay? Now, if we go back up to the chart, it says of the students who graduated from high school, 90% are happy with their present jobs. So of the students who graduated from high school, that's off of this branch, 90% are happy. So 0.90 are happy. Well, what percent are not happy then? Well, if 90% are happy, 10% are not happy. So 0.10. And we were told that of the students who did not graduate from high school, so we're looking at the lower branch now, of those students, 60% are happy with their present job, so 0.60, which means that 40% are not going to be happy. Okay, 60 and 40 make 100, in case you're wondering how I'm getting these numbers. Okay, so what I need you to understand now is if I want to figure out, so our goal is figure out the probability that a person from the junior class 10 years ago graduated from high school and is happy with his or her present job. So graduate and happy, G and H. So the probability of G and H is going to equal the probability that we are a graduate times the probability that we are happy given that we graduated. Okay? So when we look at this from the perspective of the tree diagram, we start with, well, here's the probability of, come on. Here's the I can't highlight apparently. Fine, I'll just use this. Okay, here's the probability that we graduated, so 0.85. And we're going to multiply it by the probability that we are happy given that we graduated. So that's going to be this piece right here. That's 0.90. To find that probability, we multiply those together and we get 0.765, or about 77%. Okay? Now, if I had asked you something like, well, what's the probability that you didn't graduate high school and are happy with your job? Well, the probability then would be probability you don't graduate, so 0.15, multiplied by the probability that you're happy, which would be 0.60. And so you could figure that out, the probability that we pick a junior who is not a graduate and is happy. So this tree diagram can help us answer a lot of questions, okay? But I'm going to leave it here and go ahead and let you do some practice. Whoops. Where's my screen? There we go. Now I need to stop the screen. Oh my goodness. Okay, if you're still watching this video, you're a saint, but I need to make this go away. Why can't I see how to make it go away? Oh my gosh. Okay.